So we are moving on to the next unit, which is about functions and relations and so on. Okay, so all of you know what a function is, but again, the main difference in what we are learning here is that we are learning about functions in the discrete world as opposed to the continuous world, which is sort of where most of your understanding of functions comes from. The domain of real numbers and maybe calculus. So where we talk about functions. Here we are talking about functions in the discrete world, which means functions from one set to another set. Okay, so some of these sets can be infinite, and we will talk about infinite sets later on in this lecture, in this unit. But for now, we are still living mostly in the finite world. Okay, so a function associates each element of a set A with a unique element of another set B. Okay, so the key point, one of the key points is that the association, the element that you pick in B has to be unique, right? So meaning that the same element in A cannot be paired up with multiple elements in B, right? And right, so in when you work with continuous math, you are often given things like maybe a circle, and you're told that well it can't be this does not satisfy the definition of a function because for any given value of x, there could be more than one value of y, right? So the meaning of a function is one such that y is uniquely defined whenever you pick an x. And that's the same condition that we are stating here, that once you pick some element in A, the f will map that element to just one element in B, so that something like f of x will be uniquely defined. Okay, so in the discrete world, we often represent, we try to represent functions using, these kind of arrow diagrams that I'll, draw here. Okay, so so notice that we take the example of f of x equal to x squared, right? So in this case, we are defining it as a function on natural numbers, right? So it maps one natural number to another natural numbers, right? We could have also defined it as a function on rational numbers or real numbers, but since we are doing discrete math, we try to stick with natural numbers as much as possible and not go into the other domains. So so therefore we can try to draw this. This is of course an infinite set, right? So we have natural numbers, and we can pick 0, 1, 2, 3, 4, and so on. And out here we can pick 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's put a dot, dot, dot. And then we can draw arrows to denote, to connect each element in the first set with the element to which it's being mapped. Okay, so 0 square is 0, so 0 maps to 0. Again, 1 square is 1, so 1 maps to itself. 2 square is 4, so that's the other arrow. And 3 square is 9. And 4 square is 16, which we haven't actually shown, so it's in the dot dot dot. So you can see that a function can be represented in this way, right? So by drawing arrows from the first set to the second set, okay? And the unique element thing basically says that there can be at most one arrow coming out of each element on the set on the left, right? So the arrows coming out of the points on the left, there can be at most one arrow coming out of each point. Okay, so that's the definition of a function. Any questions? Okay, so when we have a function from A to B, right? So the set A is called a domain, the domain of the function, and B is called the codomain of the function. Okay, again, these are terminology that may be familiar to you. It's not new terminology, but of course, I want to again refresh the terminology so that we can use it without people not knowing exactly what it means. So elements of A that have an outgoing arrow are called the support or the support set of F. Okay, the elements of B that have an incoming arrow are called the range. So if we go back to the previous slide, so what is the support set for this function? Going from n to n, what is the support set? Anybody can lift your hand, and maybe I'll just Greg.
It'd be the set of natural numbers.
Right. So the entire set, right? The entire A set, right? The set A, when we talk about A to B, the entire set A is the support set in this case, right? And when that happens, we refer to such functions as total functions, right? So the support set is A itself, or in other words, if you look in terms of these arrows, you can visualize that there is an arrow coming out of every point in the set, okay? And if that is the case, then you call it a total function, okay? If there are some points here that are not, from which arrows are not coming out, then we call that as a partial function, right? So it's partial in the sense that its value is defined only for some of the elements, right? So only for some of the elements in the domain, its value is defined. So that's why we say it's partially not defined. Whereas when we say totally defined, that means that for all of the elements in the domain, the value is defined. Okay, so that's why we call it a total function. So so again, going back, so I asked you what is the support set here. What is the range in this case? Anybody wants to try? Frederick.
In this case, I think it would be also the set of natural numbers.
The range is, what did you say was the range?
Oh, the range would be all the squares of the natural numbers.
Right. So all the perfect squares are in the range, right? So the range doesn't include all of n, right? So on the other hand, suppose I take, f of x equals cube root of x, okay? And taking care to, okay, so this is fine. If I say f of x equal to cube root of x, okay? Where once again, I define f to be a function from natural numbers to natural numbers. Can someone tell me what is the range and what is the support and range for this function? Well, who's gonna go? Okay.
I think the range would be the natural numbers, and the
So
support.
now I'm asking everyone to lift their hand. So if
Oh, okay.
but I'm still, it takes me some time to figure out how to call on you. So after lifting your hand, please bear with me, and then I'll. So Brian.
Sorry. I think the range would be all of the natural numbers, and the domain would be perfect cubes.
Okay, so this is an example where the domain is going to be a subset, whereas the range is going to include everything, right? Because if you talk about the output is a cube root, which means that you're mapping, so if the output is a cube root, let's erase this. I guess. Okay, so let's see here. So in this case, you're going to have elements here, and it's cube root. So we can have 0, 1, 2, 3, 4, and so on. And I'm going to arbitrarily include some elements and put dot dots for others. So we can say, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to skip a few elements, and then 25, 26, 27, 28, and then skip more. And now, if I represent the cube root function, then 0 will go to 0, 1 will go to 1, 8 will go to 2, 27 will go to 3, and so on, right? So you can see that in this case, pretty much every element on the right is going to be covered, which means that the image is the entire set. But on the left, many elements are not covered. And so the support is going to be a subset that consists of basically perfect cubes, right? So, so hopefully that gives you a good idea of what these terms mean. So, so we extend the notation of a function to sets. So if you have a set, then we simply say that f of capital S. Oops. Okay. So that must be f of capital S. Okay. So f of capital S is equal to f of x for all the x in S. So right, we take all of the points in the set S, and we apply the function to each of those points, and the resulting set is what we call as the function of the set itself. Okay, so this is a natural way of extending the function definition to sets of points. Okay, and it is sometimes called as pointwise extrapolation of the set of the function f. Okay, so so we defined the term range before. Now we are defining the term image. So image is given a set S, f of that set S is called the image of S, right? So it's basically like, okay, you are going to start from, so if S in this case is then f of S is going to be what? I'm sorry, this is not, let me just fix this. Then f of S is going to be what? I have Jacob.
It'll be the set 1, 3.
1 and what?
3.
Yeah, okay. Sometimes the volume is not loud enough for me, so let's see if I can fix that a little bit better here. Okay, so this f of S is called, so 1 comma 3 is called the image of 1 comma 27. And another way to think about image is that you start from these elements of S and you see where these arrows are, if you think of them as light rays, where they go and where they end up, that's what you think of as the image. Okay, so that's the concept of an image. So we, went through several examples already. So let's not spend time on this slide. Right, so we did all of this. So yeah, we did this too. So let's see. Can anybody tell me what is the image of this set for the function f, where f of x is square root x? Who wants to try? Let's see. I'm sorry, I have some difficulty here. Yeah. Go ahead, please.
3, 6, 2. 18.
2, 18.
32.
Yeah. Okay, so right, I mean, you probably know that 20 square equals 400, right? So if you work from there, either you can do, 18 square equals 20 minus 2 square in your head, and that'll give you 324. Or you can sort of say, okay, I need to come down by, 2 times 20 for, each time I reduce this by 1. So 324 looks like 18 square, right? And 1024 is, of course, for those of you who have done some programming, would know that 1024 is 2 to the power 10. So the square root of 2 to the power 10 equals 2 to the power 5, which is 32, right? So, okay, so composition of functions. So if you have one function f that takes you from A to B, and another function g that takes you from B to C, then we talk about a composition which is obtained by first applying f and then applying g to the result of f. Okay, and this is we use this notation g circle f or G dot F to refer to the composition. So, so now that you have seen the definition, can someone tell me what is the composition of these two functions, f of x equals 2x and g of x equal to 3x? Someone wants to try? So if you don't, Samuel.
You mean like what the end function is, right? Before I answer, I just want to make sure I'm answering the right question.
I'm sorry?
Before I answer, I just want to make sure I'm answering the right question. You mean what the end function will be, right?
Yeah, what is the composition? Yeah.
6x squared.
6x squared?
Right? Wait, no, 6x.
Okay, yeah. So G composed with F, we can call it as H, and H has this behavior that H of x equals 6x. And if you want to go through the process, then you say, okay, it is G of F of x, right? And you can read f of x from this definition. So substitute for f of x. So that's going to be G of 2x, right? And then this one says, if you apply something to G, then you basically multiply it by 3 times. So this is going to be 6x, right? So composition is fairly easy and intuitive, and something that you have done, numerous times in the past. So it's not actually a particularly new operation. But of course, the notations that we use, you have to get, you need to get some familiarity, and that's really the only thing that we are trying to, stress here. Okay, so let's take the second example: f of x equal to x squared and g of y equals square root y. And Michelle, do you want to try? You had the answer to many questions, but I somehow, whenever I clicked, it went to the wrong other person. Or do you want someone else to answer this?
I'm not sure about this one.
Sure, go ahead. It's fine, even if you don't know, right? I mean, we all make mistakes. It's fine.
Okay, I think it's, would it be x? Because like, would you substitute the x for the y?
Right. So, so basically, it's going to be in this case, let's say h equals g composed with f is defined by h of x equals x. And once again, you can do, follow the steps. So we want to do g of f of x. And then we first substitute f of x from this definition, which says g of x squared. And then we use this definition for x squared. So that becomes square root of x squared equals x. So yes, whatever the answer seems to be on the surface is exactly what it is. And when you work through the details, you realize it's exactly what you thought. Very good. So so far we have been talking about functions with a single argument, but many times we.
Also,
Was that a question?
Going back to your last example.
Yeah.
Why is it not absolute value of x?
So we have already defined everything to be a member of natural, everything to be natural numbers, right?
Okay, I thought it was integers. That makes sense.
No, so you are right that on this particular slide we haven't defined, what A, B, and C are, but I'm just going with the natural number case because that's what we have been using in the previous few slides. Okay, if not, if you are talking about integers, then yes, we need to be more clear. Again, if you're working with integers, square root is a function only if you use it to refer to the positive square root, right? Otherwise, it's not a function because it has two different values, and our definition of function says that it should have exactly one value, right? So, therefore, if you apply square root on integers, unless you take the interpretation of square root as the positive value, it's not a function. Okay, so often we work with functions that seem to take multiple arguments, right? So in this case, there are two arguments, x and y, and it's just another fancy name for addition, right? So we could, of course, define what is a binary function and develop the whole, terminology. But instead of doing that, we will instead treat a function that takes multiple arguments as a function that takes a tuple of arguments. Okay, so it just takes one argument, which happens to be a tuple, right? So in this case, it takes one argument, which is a pair, right? And then with that understanding, we would say that this function f is mapping n cross n to n, right? So this is the cross product of n with n. So that yields, these types of pairs, right? And f takes such a pair as input and produces a natural number as the output. Okay, so this is a way to, tackle any function that takes any number of arguments using the same definitions that we have developed so far. Okay, and we can extend this to any number of arguments. We can, work with real numbers instead of, natural numbers. So we can define f of x, y, z, u equals, this thing and this expression, and this is a function that takes 4 arguments, but we will again say that it takes a single 4-tuple argument, and that just keeps all of the math to be the same for regardless of the number of arguments that a function takes. Okay, so here is an example of a function that operates on Booleans, right? So far, we looked at an example on natural numbers, one on real numbers, and now on Boolean numbers. It takes 3 arguments, p, q, and r, and again produces a Boolean value. Okay, and of course we can define such a function using the Boolean operators we have looked at in the past. Okay. Any questions so far? Okay, so that's all I wanted to say about functions. So let's talk about relations. Okay, so relations are very similar to functions. The only difference is that in the case of functions, we insisted that there be at most one outgoing arrow from each element in the domain. Okay, whereas in the case of a relation, we remove that restriction, right? So the same element in the domain could be related to multiple elements in the codomain, right? So this is the definition of, this is how the definition of a relation differs from the definition of a function, okay? So an example is less than or equal to, right? Because less than or equal to, if you draw picture once again, right? And this time I will even, 1. Okay, let's start with 0, 3. Oh, what am I doing here? Okay, 1, 2, 3, and let's go with 0, 1, 2, 3. Right? And now 0 is less than, everything, right? So we can draw right? And then 1 is less than or equal to everything except 0, right? So you can see that this can get, very hairy, right? So many arrows, right? So the difference, as I said before, is that there are multiple outgoing arrows from each point in the domain, right? And so in that sense, a function is a special case of a relation where you have exactly one arrow. No, I shouldn't say exactly one. There is at most one arrow going out of each element in the domain. Then we call it a function. So a function is basically a special case of a relation. Okay. So like functions, relations associate an element of a set A with the elements of set B, and it has this difference. Okay, and typically we specify a relationship, specify a relation using a predicate, right? Because we say that there is a relation between A and B if this predicate holds on those values A and B. Okay. And just as in the case of functions, we were trying to reduce everything to binary case. That is, there is a single argument as input and single output. The same way, we are going to focus on binary relations, which have one set as the domain and another set as the codomain. We can again define relations involving 3 sets, 4 sets, 5 sets, and so on. But once again, we can, if there's a relation that is that involves multiple sets, it is easy for us to just treat it as a relationship involving products of sets, just the same way that we did in the case of functions. Okay, so this is why, again, we are going to focus on binary relations and not worry about others, because it's just a question of what is the set on which the relationship is being defined. If the set is something like a natural number, then then it's a binary relation. But if, let's say, it's a relation that takes natural numbers and natural numbers 3 times, then it will be a ternary relation. But again, we can sort of think of it as a relation going from n cross n to n. And that way, we still have just one arrow, one set on this side and one set on that side. And we can think of it purely as a binary relation. Okay, so a little bit more on the terminology. So just as with the notation that we use for functions, we use a very similar notation for a relation, except that in the case of a relation, we are using this uppercase R to denote a generic relation, as opposed to lowercase f we use for a generic function. Okay, so so we use this notation to say that R is a relation from A to B, or we sometimes use the terminology between A and B. Okay, but if you have a relation that happens to be from a set to itself, then we use the term that it is a relation on A. So if you have a relation R that takes A to A, right, then we will call this as a relation on A. Okay. Again, some simple terminology. The domain and codomain terminology is exactly the same as we had for functions. Okay, and we use this notation A or B to denote that A and B are related by R. Okay, and when they are related by R, once again, pictorially, we will draw an arrow from A to B, right? So we so once again, if let's say, let's define a relation R taking N to N, okay, where why don't I do this? Okay, so we can define, a relation like that. A and B are related if they are, or maybe let me just, yeah. So if they are related, if they are either equal or B is, one higher than A. Okay, so then we can again draw the picture 0, 1, 2, 3, 4, 5. Then again 0, 1, 2, 3, 4, 5. And now, we won't have quite as many arrows, right? So 0 goes to 0 and 1, 1 goes to 1 and 2, 2 goes to 2 and 3, and 3 goes to 3 and 4, 4 goes to 4 and 5, and so on, right? So, so once again, we use these arrow diagrams to, depict these relations and get a sort of a visual idea of what the relation is doing. Okay, so we can define the notion of an image for relations in exactly the same way we do it for functions, except that in the case of a function, if you say f of a, then f of a will be exactly one value. In the case of a relation, if you say R of a, that can be a set of elements because, again, in this picture, if you pick one element, that could be mapped to multiple elements on the right-hand side. Therefore, when you take R of, if you take one element and see what its image is, there could be multiple elements on the other side. Okay, so except for that, the definition of the image of a set remains exactly the same as in the functions. And visually, you can say, okay, if I have a set, I pick all the elements of the set on the left, and then I take the arrows from each of those elements and see which elements I get to on the right. And now I put all those elements together, and that is the image of the original set. Okay. So, so a graph is the term that we use for referring to this picture. Okay, so this is what we call as a graph of the relation R. Okay, so just a visual way of representing it using arrows. Okay, so again, I've already shown these examples before. Graphs representing a relation, and again, the key difference in a graph representing a function is that for any point here, there will be, at most one out arrow. That is the key property of a function. Okay. So thinking about relations and functions based on this arrow property, we can make the following observation, right? So something is going to be a function if it has a less than or one arrow out property. Okay, so what is an arrow out property? So we are counting the number of arrows going out of a point. Okay, and we are saying that number is less than or equal to 1, right? Then it's a function, right? Because that's we are trying to say that, okay, some points may not be mapped to anything on the right. So they may have 0 arrows going out, and others may have 1 arrow going out. And as a result, whenever we say that a function has less than or equal to 1 arrow out, that must be a function. Okay, and if every point on the left has at least 1 arrow coming out, then that means that there is an image for every element in the domain. Okay, or in other words, the support set is the entire domain, and so we call that a total, right? So again, we can think of if every point in the domain has at least 1 arrow coming out, then it's a total function, right? Or a total relation. So total function means, okay, a total function will satisfy both these conditions, whereas something that just satisfies the total condition here is a total relation, right? Because in addition to be a function, it has to satisfy that property. Okay, so now 2 new terms or 3 new terms, which are very important for understanding infinite functions, infinite sets, which is what we are going to look at next. So surjective means now we are looking at the right-hand side. So, and we are looking at how many arrows are coming into each point on the right-hand side set. And we are saying that if the number of arrows coming into each point is at least 1, okay, which another way of thinking about is that you have covered every element in the codomain, right? Something is coming into every point in the codomain, so you have basically covered everything in the codomain, and then we call that as a surjective map, okay? A surjective function or a surjective relation, okay? So we say that something is injective if it has, less than or 1, arrow property, okay? So this means that so what this means is that the number of elements on the left, right, is in a sense So what this says is that there is no more than one arrow coming into a point. Okay, so notice that that means it could have 0 or 1. Okay, so if it is 0, that means, well, nothing in the domain maps to this element. Okay, so some elements of the codomain may be left out. Okay, so this is the reason why we call this as injective. Okay, and bijective means that the relationship has both properties, which means that if you put these two properties together, it says greater than or equal to 1 arrow in, less than or equal to 1 arrow in. Well, if both of them are true, then it must be the case that there is exactly 1 arrow coming into every point. Okay, and you can see that if you have exactly 1 arrow coming into every point, okay, okay, so if we are talking about functions, okay, which we typically, when we talk about injection, surjection, and so on, we typically talk about functions. And therefore, when we have exactly one incoming property, that means there is each arrow matches up one element on the left with one element on the right. Okay, and it has to be a one-to-one mapping because you have, if it is a function, then there can be only one point. There can be only one arrow going out of a point here, right? And injective and surjective says that there is exactly one point coming into each point, one arrow coming into each point on the right, which means that each arrow represents a kind of a pairing or a matching between points on the left and points on the right. And this is how we will do counting, right? We'll say that, okay, so this defines a way of saying that both sets have the same number of elements because these arrows are creating a one-to-one pairing of each of the elements. Okay, so so another terminology for injective is one-to-one, right? So because it basically says no element on the left can map to okay, this basically says multiple elements cannot map to the same output. Okay, so so therefore, if it's a function, you end up with a case where it is one-to-one, right? Because you think about this, right? So let's take a point on the right. Okay, there can be only one arrow coming into it, right? Now look at another point. Okay, so if the arrow is coming from the same point, this won't be correct because this will no longer be a function. Okay, so if it's a function, then we know that that's not going to work. So it must be the case that it must be coming from another point. Okay, so this is why we use the term one-to-one to say that each element on the left gets mapped to exactly gets mapped to a unique element on the right. Okay, so so when you have this one-to-one property, then you can do many things such as inverting the arrows, and then basically you have what is called the inverse of a function, and the inverse of the function is well defined because because there is exactly one element is being paired with one element. How does it matter whether the arrow goes from left to right or right to left? the properties of the graph will be the same regardless, and therefore, even if you flip the arrows, you will still have a function that goes from right to left instead of the original function which went from left to right. Okay. Okay, so so let's have this understanding of surjective and injective, and your unlike some of the notions we have seen so far, such as domains and codomains and ranges and so on, those are, I think, easier to get your wrap your head around, whereas injective and subjective is going to take a little bit more time to fully internalize. But that's okay. We will have more examples, and we will go through that concept for quite some time, so you actually can, in fact, understand it well. So, so based on the notion of surjective, injective, and so on, we define 3 terms. Okay, so remember that what we were saying here is that given a particular function, okay, we were saying whether that function is surjective, and the way we were doing that is by drawing these arrows and then checking some properties on these arrows in terms of how many arrows go out of each point on the left and how many arrows come in into each point on the right. Okay, whereas these do not specify a function, but simply say if there is a function, okay, then we say that this relationship holds between A and B. Okay, we say that A surj B if and only if there is a surjective function from A to B. Okay, what this means is that notice that we are talking about functions. Okay, therefore, if you have a surjective function, that means there is an arrow coming into every point in B. Okay, and this arrow, right? So surjective means, okay, if these are, let's say, 3 points, then there is 1 arrow coming in here, maybe 2 arrows coming into this, and maybe another arrow coming into this. So this is the codomain, right? So in a surjective map, there will be arrows, right, greater than 1 arrow coming in to every point, right? So that is a surjective map. So you can see that in a surjective map, the support set seems to be somewhat bigger than the codomain, right? Because we know that there is an arrow coming into every element in the codomain, and the corresponding, these arrows that are coming into each of these points may be coming from, there may be 1 arrow coming in, or there may be multiple arrows coming in. So the total number of arrows, right, which corresponds to the size of the support set, right, that is greater than the number of points in the codomain. So if you think of counting the elements on the left and on the right, then you can see that the elements on the left should clearly be larger than the number of elements on the right, right? Because for every element, there is at least 1 element on the left, right? So therefore, if you count 1, 2, 3, then there must be at least 1, 2, 3 elements on the left, okay? So this, we are going to use this reasoning to that surjective maps cover all of the codomain, and therefore the support set should be bigger than the codomain size, which means that the size of the domain itself should be larger than or equal to the size of the codomain. Okay, so what we do here is we are going to say that the size of A is larger than size B if there exists a surjective mapping from A to B, right? Because we have a mapping, we have a set of arrows from A to B that cover everything in B. Okay, so therefore, if you're able to cover everything in B, that means A must have more elements. Okay, and in a similar way, you can reason through this, and you'll find that if if it's an injective mapping, then the size of A has to be less than or equal to B, and if the sizes are the same, then there has to be an exact pairing between the elements, or else you cannot or else you cannot cover all the properties of bijection is that you have an exact pairing of each element on the left with each element on the right, which is possible only if the two sets have the same number of elements. Okay. So okay, so I'm going to give you an example of how you're going to use bijections to count the sizes of sets. Okay, and this technique of using bijections or surjections to compare sizes or count sizes is most useful when we deal with infinite sets. Okay, but sometimes it's also useful for finite sets, and as an example, we will look at the power set example again. Okay, so we have a set A, and sometimes when we write with hand, we just write POW of A because writing out those script characters by hand sometimes is challenging. Nobody other than the person who wrote may be able to tell that it's a script character. So so what we can do to do this counting is the following. Okay, so define a map, or let me just call it a function from from power of A to okay, so binary strings means strings of zeros and ones. Okay, or you can think of them as binary numbers, right? It doesn't really matter. So what we are going to do is that right? So these binary strings are going to have the same length as the number of elements in A. Okay, and the way we are going to do this mapping, right? So again, a function from power set of A means that we are going to define, that means we are defining f of x for some x that's a subset of A, right? Because the power set contains all the subsets of A. Therefore, if you are defining a function from the power set, that means we are defining a function that takes a subset of A as an argument. Okay, and we have this mapping which basically says that so f of x contains a 1 in its ith position, right? If and only if, let's call this right. So let's say A contains elements A1 through AN, then right? So we are constructing this binary string based on the contents of this set X that you want to map to, okay? And the construction is simple. If the
Professor, you froze. We can't hear you.
Professor? I can't hear you.
okay, so can you?
I can hear you. You're not frozen anymore.
Okay, good. So Zoom crashed on me. So anyway, all I wanted to do at this point is that we are reaching the end of the class. So why don't we pick up from where we left off in the next lecture? And then I will, of course, answer any questions that you may have. But other than that, we can wrap up for the day.
I had a question about for bijective. Bijective means it has one arrow out and one arrow in. But what forces it to only have one arrow out?
Okay, so if it's a bijective function, okay, so then, so typically we talk about functions when we are talking about surjective, injective, and bijective, and that's what makes it. So we'll say one-to-one function.
Okay.
For instance, in the case of injective, we'll say one-to-one function, and then any other questions? Okay, so we will meet again next week.